What happens when you have an electromagnetic wave coming to a boundary between two non-conducting linear media at an oblique angle, non-normal angle? Hi, this is Jonathan Gardner. We're covering section 8.2.5 of Griffith's Introduction to Electrodynamics, second edition. Here we're going to examine what the waves that are plane waves that are coming into the boundary at an oblique incidence look like and what happens. So the setup is as follows. So just like before, we have epsilon 1, mu 1, n1, v1 on the left side, epsilon 2, mu 2, n2, v2 on the other side. And we're going to use three different colors. So hot pink is the incoming incident wave traveling in this direction. That makes an angle with the x-axis of theta I. This is the incident wave. Then we have a transmitted wave. It makes an angle theta t with the x-axis. And then we have the reflected wave. Makes an angle theta r, moving away from there. Now we're going to use kappa vectors. Kappa vectors, as you recall, the length is determined by the wave number. The direction is determined by the direction of the wave. And the formulas for these three waves are written out as follows. So EI vector complex takes an R vector, a time component. This is equal to E naught I vector complex. This has the polarization of the electric wave. And then it's taken to the E to the I kappa I dot R vector. These are vectors minus omega I t. And the B vector, the B field of the incident wave, is just 1 over V1 times kappa I hat cross the E field. Okay, the reflected wave, let's do that in green. Where did my green go? There it goes. Is equal to E naught R vector complex, E to the I kappa R dot R vector minus omega R t, and the B field of the reflected is also complex, 1 over V1 of kappa R hat cross E R vector complex. And I forgot a complex sign for the incident waves. Let me fix that right now. Okay. And the transmitted wave is the same thing. Minus omega t, and the bt is also a function of r and t, 1 over v2 kappa t hat cross e t vector complex. Okay, and the total E field is just the incident plus the reflected, and it's the transmitted for x is less than 0, for x is greater than 0, and the B field is the same thing. Equals BI plus BR for x is less than 0, and then it's BT for x is greater than 0. Okay, that's all the electric fields and magnetic fields. So all we have left to do is find these 9 constants. 1, 2, 3, 4, 5, 6, 7, 8, 9. All right. Immediately we can start applying the boundary conditions, but the boundary conditions are going to give us a general form that looks like this. It's going to be something e to the I kappa incident vector dot r vector minus omega I t plus something e to the I kappa reflected vector dot r vector minus omega r t is equal to something e to the I kappa transmitted vector dot r vector minus omega t t. Okay? And just like before, if we hold everything else constant and vary time, all these terms must line up with each other in order for it to be equal. And so we're left to conclude that e to the minus I omega I t is equal to e to the minus I omega RT, which is equal to e to the minus I omega TT, which says that the omegas are all equal. We'll just call that omega. And so from here, because the omegas are equal, we can say that the kappa incident has to equal the kappa reflected. We'll just call that kappa 1 for the left, and the kappa transmitted has to be kappa 2. These are magnitudes. These are the magnitudes of these vectors. The directions are, of course, going to be different, given by the angle of the angle with makes with the x-axis. Let's draw this. Yeah, this will be just constant. Okay. Now the first thing that that's interesting, that's different than what we did last time, is let's suppose. Oh, the other thing. So that's the omegas. Let's do the k's. So by similar logic, we can say that e to the I kappa I dot r vector has to equal e to the I kappa r vector dot r vector has to equal e to the I kappa t vector dot r vector. Okay, and so this says that basically kappa I dot r has to equal kappa r dot r has to equal kappa t dot r. Okay, and for x at x equals to 0. Okay, that only applies at the boundary conditions right here. That's what we're applying the boundary conditions, so x equals 0. So this says that the y component, so kappa I in the y direction times the y value has to equal kappa r in the y direction times the y value has to equal kappa t vector in the y direction times the y value. So obviously all these vectors have to have the same they have to have the same value for y. Otherwise the equations won't line up and you won't have boundary conditions that'll match. Now there's 3 interesting results when you look at this very hard. Okay, first of all, we can take any incident wave and transform the coordinates so that that incoming wave lies in the xy plane. Okay, so if the incident wave, for instance, is coming down at the same time it's going up, so it's coming down and up like this. Let's see if I can draw that better. Down and up like that. Then all we do is just rotate it so that now it's coming in the xy plane. And the fact that it's coming in the xy plane means it has no z component. Oh, this is also true for the z's. This is also true for the z's. So basically, if the incoming wave has no z component, none of the others have any z component. Okay. So we're just going to assume that we're going to align everything so that the xy plane contains the incoming wave direction. So it'll contain all the other wave directions as well, and all their y components must be equal. Okay, so the conclusions. Number 1, A in the book is that you have a plane of incidence. So the plane of incidence is that plane which contains all of the kappa vectors, all the wave direction vectors. And it is a plane. It also contains a normal to the boundary. Okay, so x I hat or x would be the normal to that surface. The second thing that we get is if you look at how these two guys relate to each other, and the fact that, well, let's write out the y component of kappa I. So kappa I in the y direction, what's that equal to? Well, that's the magnitude kappa I, and then the angle that it makes there, well, that's just sine of theta I. Okay. And then kappa r in the y direction, well, that's just kappa r times sine theta r. Now these two things have to equal each other, and these two things equal each other because, as we said before, you know, they have the same omegas, and since they're in the same material, they must have the same magnitude, right? And so we're left to conclude that theta I must equal theta r. This is the angle of incidence must equal the angle of reflection. And the third conclusion we can draw, C, has to do with how this relates to that, how the incident y component relates to the transmitted y component. So let's write that out. So we have kappa I sine theta I has to equal kappa t sine theta t. Well, kappa I is related to kappa t by the material, right, that it's in, and they have the same omegas, so we're able to rewrite this as sine theta t over sine theta I is equal to n1 over n2. This is Snell's law. Okay, so this is another important result. We'll actually be using this as we try to find the magnitudes. So those are the three interesting results, and he says it's remarkable because we didn't actually apply any of the boundary conditions in particular. And it really doesn't matter what the boundary conditions are, as long as they say something times these waves are equal to something times those waves. And given that, we're able to draw these three conclusions that, you know, contain a surprising amount of information. So basically, we've already calculated all of these 6 constants, right? We know that all the omegas are equal. We know that the kappas have to relate in a particular way. All right, now to calculate the E knots. This is actually quite easy. I'm going to start a new page here, even though I probably shouldn't to save trees, but oh well. So the first boundary condition says that the D fields have to equal in the perpendicular component. So we have epsilon 1 times E naught I in the x direction plus E naught R, these are vectors, in the x direction has to equal epsilon 2 times E naught T, vector complex, in the x direction. The perpendicular D fields have to equal each other. So this one basically boils down to the conclusion. The perpendicular component, well, that's going to be the magnitude of E naught I times, well, this is going to be negative sine theta I. Why is that? Well, let's go back to our picture. The angle of incidence, so this is theta. The E field is pointing perpendicular to that. Oh, I forgot the assumption that we're making at this point. At this point, we're making an assumption that we're dealing only with the E field in the plane of incidence. So we're dealing with parallel polarization. There's another problem, 8.16 in the book that I would like you to approach and solve, that handles the case where the polarization is perpendicular to the plane of incidence, but we're doing parallel now. So what is the E field? Well, the E field is pointing perpendicular to I, to the angle of incidence. Let's see if you can see that in there. So it's pointing perpendicular. You do your trigonometry, and it turns out to be negative sine theta I times the magnitude of the E field. Okay, and then the ER is the magnitude E naught R. I'll just write it out that way without the vector sign, times sine of theta R. And that has to equal E2 over E1. And then this is going to be E naught T, the magnitude of that vector, minus sine theta T. Okay. And that simplifies to what does it simplify to? Oh, this. So we get E naught I complex equals to minus E naught R. I'm skipping something here, and it's important. Oh, let's ignore that for now. Let's go on. Okay, number 2. The perpendicular component of the B fields have to be equal to each other. Well, that's trivially satisfied because the B fields are pointing, you know, perpendicular to this plane of incidence. So there's no X component for the B field. So this is trivial. Gives us nothing. 3 says that the Y and Z components. Well, there's no Z component of the E field. But so the Y components of the E field, so E naught I times, what's the Y component? That's going to be cosine theta I. Plus E naught R, cosine theta R, has to equal E naught T, cosine theta T. Well, theta I and theta R are equal, so this basically says E naught I plus E naught R is equal to cosine theta T over cosine theta I E naught T vector. Okay, we're going to call this dude alpha. Okay, E naught T complex, not vector. The the last one, number 4, relates to B fields. And if you work through the B fields, you're going to get this. You're going to get 1 over mu1 v1 times E naught I complex minus E naught R. This is easy because the B fields are pointing in the Z direction, so it is going to be equal 1 over mu2 v2 times E naught. Okay, so the reflected B field is pointing down, the incident and transmitted are pointing up. Okay, and so the Z components are equal to each other. These are the Z components. And so we're just left with EV familiar E naught I complex minus E naught R complex equals mu1 v1 over mu2 v2 times E naught T complex. Well, those are two equations that look similar to the ones we've had before. Where'd my yellow one go? Got a nice yellow one that I was using. We have this guy. Looks a little different. It has that new alpha constant. We have this guy, where we just use the same substitution for beta. So this is equal to beta. Okay, and so for solving for these, we get the following results. We get E naught R is equal to alpha minus beta over alpha plus beta E naught I. And we get E naught T is equal to 2 over alpha plus beta of E naught I. Okay. Is that correct? That's correct. These are called Fresnel's equations. These are some of the Fresnel's equations. There's more. Interesting to note. The alpha, where'd alpha go? Alpha's up here. Well, theta T can be rewritten in terms of theta I because we have the relation that we calculated earlier. If I can see if I can find it over here. Here we go. We have this relation that relates the n1 and 2 to theta I and theta T. Well, we can basically rewrite theta I as a equation with terms based on theta, or we can rewrite theta T in terms of theta I. And so we could actually reduce alpha equal to square root of 1 minus n1 over n2 sine theta I, all that squared, divided by cosine theta I. Okay, and if you draw a graph for this alpha, and when you bring your theta, when you bring theta I to 0, what happens here? Well, this is just 1 minus 0 divided by 1. That becomes 1. That's the case what we solved earlier. Okay, a couple of graph terms. All right, first graph. That's interesting. This is a graph of the ratio of the transmitted and reflected E fields. Okay, so we have E naught T over E naught I. And down here we have E naught R divided by E naught I. And it looks something like this. Okay, so at 90 degrees, that's when the wave is coming in parallel to the surface. We get no transmitted wave and complete reflection. So reflection is all the way up here, and transmitted is all the way down there. Okay, but at this angle, we get a certain amount of. I should mention this is a graph I'm copying from the book. This is based on air to glass. Okay, different materials will behave differently. This reflected one goes down like that. Okay, this is air to glass. This angle here says that the reflected is 0. Okay, this is where alpha is equal to beta. And if you look at the equation for the reflected angle, that means the reflected electric field has to be 0. Okay, so this graph says that at that point, alpha equals beta, and so reflected is 0, and we call this Brewster's angle. Okay, Brewster's angle is calculated with this formula. Is equal to 1 minus beta squared all over n1 over n2 squared minus beta squared. Okay, and if you make the simplification, mu1 equals mu2 as it is for most materials, then you can reduce this all to tan theta b is equal to n2 over n1. Okay, Brewster's angle. Next interesting bit to talk about. This is, there you go. That'll help you a little bit. Oh, just as before, when you have a negative, when beta is greater than alpha, then that means E naught R is going to be negative. Well, rather than having the magnitude be negative, just say it's 180 degrees out of phase. It has a phase shift of 180 degrees. All right, intensity. Intensity on the boundary is, for the incident wave, is 1/2 E1 V1 times E naught I squared times cosine theta I. Okay, we're not taking the full intensity of the wave, we're taking the intensity of the wave hitting that surface. And now we have to match the intensity of the reflected wave and the intensity of the transmitted wave. So the intensity of reflected wave will be given by 1/2 E1 V1 E naught R squared times cosine theta R. Remember, theta I equals theta R. And the intensity of the transmitted wave is 1/2 E2 V2 of E naught T times cosine theta T. Okay, so if we were going to calculate the reflection coefficient, that's the intensity of the reflected wave divided by the intensity of the incident wave, we end up with basically E naught R over E naught I, which is just alpha squared. That should be rather easy. The angles are equal, the constants are equal. But for the transmitted coefficients, transmission coefficient, that's the transmission divided by the incident, that is going to be E2 V2 over E1 V1, which, E naught over T squared, and then the cosine theta T. So cosine theta T over theta I, you can reduce this down to the simple formula. Alpha beta 2 over alpha plus beta squared. Okay? And if you draw a graph, this is what the graph would look like. So the transmitted would be, it'd go up a little bit at Brewster's angle, then it'd go down to 0 at 90 degrees. This is at Brewster's angle. And this one would go up, and then go down, and it'd go all the way up to 1. Okay, this is reflection, this is transmission. Okay, there's not much more to say on this. I don't want to spend too much time beating a dead horse here. Hopefully this is enough for you to understand everything. And if you have any questions, be sure to comment or make a video response, and I'll try to get back to you. Thanks for your time. Bye.